Welcome to Module 4. You can now write smart contracts, but how do you compile them? How do you test them before deployment? How do you actually get them on the network? This module is all about the complete life cycle, from code to deployed contract. We're going to use Foundry, the modern Ethereum development toolkit that has become the industry standard. By the end of this module, you'll be able to set up a professional development environment, write and run tests, deploy to networks, interact with your contracts, and verify your code on the blockchain. Let's get building. First, what exactly is Foundry? Foundry is a modern smart contract development toolkit, and it's become the standard for serious Ethereum developers. It's written in Rust, not JavaScript. This makes it incredibly fast. Tests that take minutes with other tools run in seconds with Foundry. It's Ethereum-native. Every design decision prioritizes smart contract development. It understands the EVM deeply. Foundry includes 4 tools. Forge, the main tool. It compiles your contracts, runs tests, builds artifacts, and deploys to networks. Cast, this is the CLI, or command line interface, for interacting with your contracts. You can read contract state, send transactions, all from the command line, no front end needed. Next is Anvil. This is a local Ethereum node, perfect for development and testing. Next is Chisel. This is a Solidity REPL. You can write quick snippets of Solidity and test them interactively. There are 3 reasons experienced developers choose Foundry. First is speed. Forge is faster than competitors like Hardhat. Tests run quickly and development is rapid. Second, testing quality. Foundry's testing framework is designed for security. It supports fuzz testing, invariant testing, and fork testing, advanced techniques that you need for robust contracts. Third is its EVM proximity. Foundry is close to the metal. It understands gas costs, bytecode, and compilation details. If you care about optimization and security, this matters. Setting up Foundry is simple. It's a one-line install. You run the command on the screen, and this downloads and runs FoundryUp, the official Foundry installer. It installs all 4 tools: Forge, Cast, Anvil, and Chisel. This works on Mac OS X, Linux, and Windows via a Windows subsystem for Linux. In Module 3, you learn Solidity syntax. Now we're going to organize it. In a Foundry project, you store your contracts in a source directory. Nothing fancy. Here's a simple vault contract that we'll use throughout this module. Let me highlight the key decisions. The deposit function is external, not public. Why so? It's slightly more gas efficient since it can't be called internally. This is a professional optimization pattern. Both functions emit events. This is non-negotiable. Events are how off-chain systems know what happened. Every state chain should emit an event. The events are indexed on the user address. This lets off-chain systems filter by users efficiently. Notice the withdraw function uses require checks. This is basic validation. More sophisticated contracts use custom error types, but this is the foundation. This is production quality contract structure. Everything you see here, visibility choices, events, error messages, follow professional patterns. Store this in simplevault.sol and we'll compile it next. To compile, you simply run forge build. This single command reads all Solidity files in the source folder, compiles them to bytecode, generates artifacts for the compiled output files, and saves everything to the out folder. Compilation behavior is controlled by a foundry.toml file. Let me explain each setting. Solc equals 0.8.20 means this uses the Solidity compiler version 0.8.20. Optimizer equals true enables the Solidity optimizer. This is important. Optimizer runs equals 200 is a parameter for how aggressively to optimize. 200 is a good default. Why does the optimizer matter? Well, the optimizer reduces bytecode size. Smaller code means cheaper deployment. It lowers our gas costs because optimized code runs more efficiently. And it changes the bytecode hash. This is critical for verification. The compiler must use the same optimizer settings you did, or the bytecode won't match. If compilation fails, Foundry will show you the exact error. Compilation is the first step. If your Solidity has syntax errors that caught here, fix them and move on. This is the most important slide in this module. Before you deploy to the blockchain, before your code touches any real money, you must test it thoroughly. In Foundry, tests go in the test folder. Here we can create a simple vault.t.sol file. Let's break this down. We import /standard/test.sol. This imports Foundry's testing framework. It gives you assertions, utilities, and testing helpers. Then we import our contract, source/simplevault.sol. Then we create a simple vault test contract and inherit Foundry's testing.sol contract. The setup function runs before each test. It's where you initialize state. In this case, we deploy a fresh simple vault contract for each test, as well as set up each participant in the tests with some ether. This ensures tests are isolated. One test can't affect another. Any function that starts with the keyword test is executed as a test. Here we can see the test deposit function. This tests the contract's deposit function. Inside, we have a function call that calls vault.deposit and passes the specific value that we want to pass. In this case, 1 ether. The assertion then checks that the balance of the contract was correctly updated. To run tests, we run forge test to execute the entire testing suite. This spins up a local EVM, runs the setup function before each test, and executes each test function. It reports successes and failures and shows gas usage per function. Testing in Foundry is not optional. Professional developers write tests for every function, every edge case, and every fail scenario. Before you deploy, you must have high test coverage. This protects your users and it protects your reputation. Tests are your safety net. Write them and run them. Fix failures and only then deploy. Now let's look at what happens when you run tests and some advanced testing features. Forge test is the basic command. This runs all tests in the tests folder. Each test shows whether it passed or failed and the gas used. Foundry includes powerful testing techniques. Fuzz testing is a type of testing where instead of writing individual test cases, you specify a property and Foundry generates random inputs. It's incredibly effective at finding edge cases. Invariant testing is where you define invariants, properties of the protocol that must always hold true, and Foundry tries to break them. If your contract has an invariant bug, fuzz testing will find it. Then we have fork testing. You can test against the real mainnet state. You can deploy your contract against a fork of mainnet and test how it interacts with the real contracts. This is advanced, but critical for serious security work. Your tests have now passed. Now you deploy. But deployments need to be deterministic and reproducible. This is where deployment scripts come in. Here we can see an example of a simple deployment script. Let me explain the key parts. First, we import the script framework, which gives you special functions like the vm.startBroadcast function. This tells Foundry, starting now, I'm sending transactions to the blockchain. Use my account for this. We deploy a new simple vault, and then we stop the broadcast. This is, I'm done sending transactions for now. Why do we use this pattern? Well, scripts are deterministic. Running the script twice gives the same result. It will generate the same deployment address. Anyone can run the same script and get the same deployment. You can test scripts locally before sending real transactions. This makes them incredibly safe. If your contract takes constructor arguments, the script passes arguments exactly as needed. In production scripts, you log the deployed address. This is critical for record keeping. You need to know where your contract was deployed. Deployment scripts are how professionals deploy, not ad hoc commands, not clicking buttons. Reproducible, version-controlled code. There are two deployment paths, local development and testnet. Let's walk through both. For local development, we'll be using Anvil. Anvil is a local Ethereum node, perfect for development. To start it, we simply type the keyword Anvil. This starts a local blockchain on your machine. It prints some pre-funded accounts, and in another terminal, you can deploy your contract. In this case, the RPC URL points to your local Anvil node. You can now interact with your deployed contract using Cast. This is zero risk. You're developing on your own machine. When you're ready for the real thing, but not mainnet, use a testnet. Sepolia is Ethereum's current testnet. Step 1. Set your account up securely. Never ever put a private key in plain text. Use Foundry's secure key management. You'll be prompted for a private key and a password, and your key is safely encrypted and stored in Foundry key stores. Next, we deploy to Sepolia. Let me explain each flag in the above terminal command. RPC URL $Sepolia RPC URL points to a Sepolia RPC endpoint, like in Fura or Alchemy. -- account space my account uses the secure account you imported earlier. -- broadcast actually sends the transaction. Without this, it just simulates what would be. Step 3, we verify. After deployment, you'll see contract deployed to and your contract address, as well as the transaction hash. Save this address. You'll need it to verify and interact. Why these two paths? Well, local testing is fast and free. Testnet testing is more realistic. It's a real blockchain, but costs testnet ETH, which is free to get from faucets. Always test locally first, then testnet, then mainnet. Once deployed, you interact with your contract. Cast is the CLI tool for this. There are two types of calls. Cast call is a read-only. It just queries state, doesn't change anything, and it's free. Cast send is state changing. It sends a transaction, costs gas, and modifies the blockchain. Why cast? Traditional workflows require a front end. You need a Web3 library, React, and MetaMask integration. Cast needs none of that. It's pure CLI. Perfect for developers testing locally, backend engineers integrating on-chain data, scripting interactions, and debugging. For complex function calls with many arguments, you can encode manually. Cast is your Swiss Army knife contract interaction. Learn it, and you can work with any contract from the command line. Your contract is deployed, but the world can't see your code. Verification solves this. Verification uploads your secure code to Etherscan or another block explorer in a cryptographically proven way. Here's how it works. You provide your source code. Etherscan recompiles it using your exact compiler settings. If the recompiled bytecode matches the bytecode on-chain, verification succeeds. Your source is now publicly visible. And why does verification matter? Well, there are three critical reasons. The first is trust. Users can read your code before interacting. They can see there's no hidden logic trying to steal their money. Second is auditing. Security auditors need source code to review contracts. Without it, they can't work. And third is standards. Any serious contract on mainnet is verified. It's expected. Verification isn't non-negotiable for production. Once verified, users can inspect your code forever. Before we finish, I need to talk about security at a level we haven't yet. Your private key is the most sensitive thing you own. If someone gets it, they control your accounts and they can steal everything. Beginners often store private keys in plain text. Never do this. This is a disaster. If someone sees your .env file, they own your money. The solution is encrypted storage. Foundry has a secure solution. Cast wallet import -- interactive. This prompts you to enter a private key with a hidden input, set a password as a hidden input, and then create an imported named account. Now you reference your key by name, never the raw private key. This is not paranoia. Countless developers have lost fortunes to poor key management. Treat your private key like your house keys. Keep it secure and never expose it. Let me summarize professional Foundry practices. Testing first. The mindset is test-driven development. Write tests before you deploy, or write tests immediately after. Aim for high code coverage with a minimum of 80%. Critical functions should have 100% coverage. Test edge cases. 0 values, max values, negative cases, boundary conditions. Use fuzz testing. Let Foundry find bugs you didn't think of. And then secure key management. I can't stress this enough. Never store private keys in plain text. Always use cast wallet import -- interactive for local development. Use secret management in CI/CD and never commit .env files with keys to Git. Always use a .gitignore file to exclude sensitive files. Keep scripts in the scripts folder. Organize them logically. Make deployments idempotent. Running twice shouldn't duplicate contracts. Log all important information, addresses, transaction hashes, and timestamps. Keep deployment records for audits. Before deployment, write comprehensive unit tests. Every function, multiple test cases per function. Test all edge cases and failure scenarios. What happens if someone passes 0? What if they pass the maximum value? Aim for 80% code coverage and use forge coverage to check. Always do a security review. Check for reentrancy issues. If your contract calls external contracts, could they call you back maliciously? Verify access control, and every privileged function should have guards. Audit event emissions. Does your contract emit events for all important state changes, and will off-chain systems stay in sync? Then do your deployment checklist. Use cast wallet import for secure key storage. Verify your contract source on-chain with Forge Verify, and always test on Testnet before mainnet. Log all deployment addresses. Save this information. You'll need it for audits, upgrades, and integrations. You've now learned the complete smart contract lifecycle. Foundry is the modern Ethereum development toolkit. Learn it and use it. It's the industry standard. Next, we'll cover security in depth. We'll learn about vulnerabilities and how to avoid them and how to audit contracts. But first, you have the foundation. You can write real contracts, test them, and deploy them. That's huge. Great work completing Module 4. Now you're a smart contract developer with professional practices.